Gina Kamben from the Head of Monitoring, Review and Reporting UN Convention on Biological Diversity. Gang Liu, Professor, University of Southern Denmark, Department of Green Technology. And Rohit Nishant, Associate Professor of the University of Laval, Department of Management Information System. And finally, Andreas Frommert, a Senior Researcher at ETH Zurich, Department of Ecological System Design. So the artificial intelligence has been increasing lately, and it offers many opportunities for industrial ecologists, but it also poses new challenges. And today's presentation will give an overview on the kind of opportunities and challenges of AI in the context of industrial ecology. So thank you very much. And now I would like to start with the first presenter. Is Buzal here? Ah.
Yeah, I'm here, but I think I just seen your record about my presentation.
Yeah, is there a problem for this?
Oh, it's a video. It's an MP4 file, I think.
MP4 file. You already record. You can share the MP4 file. It's okay, no problem. You can just we are recording the session. You can just share your video if you want.
Oh, okay, okay.
No problem.
Okay, I can. Actually, I can just do my presentation. Yeah, because it's midnight for my side. Sorry.
Yes. We know it's very, very difficult.
Yeah. Okay. Can you see my screen?
No.
Oh, sorry.
Yes, now we can see your screen.
Okay.
You can maybe share in full.
Yeah, sure.
Yeah.
Can you see that?
Yeah, we can see the presenter view mode now.
So.
Maybe you can click the swap display, I think. Just the bottom neck too.
Yeah. Just hold on a second. Sorry. Yeah.
Hi.
Okay, great.
Okay, thank you. Sorry for the delay.
Yeah, please. Thank you very much.
Okay, we'll start right now. Okay, thank you so much for the patience. And good afternoon. My name is Bu Zhao, and currently a PhD candidate from School for Environment and Sustainability, University of Michigan. Yeah, today I'm pleased to share an ensemble of our group's current studies. The topic of today's presentation is estimation of unit process data for life cycle assessment using machine learning approach. As we all know, life cycle assessment applies life cycle thinking to evaluate the environmental impacts of a product system from all unit processes of its whole life cycle. A key step in LCA is life cycle inventory analysis, which constructs an inventory of energy and material exchanges and environmental emissions in each unit process of the product life cycle. A comprehensive LCI is the foundation for a successful realization of LCA studies. However, collecting data to compile a complete LCI is often a major challenge for LCA research and practice. Consequently, incomplete LCI can lead to inaccurate and even erroneous LCA results. Currently, the development of LCI still heavily relies on collecting empirical data from multiple sources. For example, like on-site investigation from lab, from surveys and even literature reviews. All these methods require substantial labor and financial investment. So it's urgent for us to find more efficient method to fill the current data gap. And recently, due to the rapid development of data science, alternative approaches using machine learning techniques have been used to address the current data challenges in LCA studies. So in this study, we are trying to develop a computational framework for estimating the missing LCA data based on the existing data. Specifically, we developed two supervised learning models using different techniques. The first one is a similarity-based framework, and another one is a decision tree-based. Both of these methods estimate missing unit process data solely based on limited known data without relying on additional empirical data. The data set used in our studies are the unit process data from Eco-Inventory, which is one of the most comprehensive and international LCI database. After the data pre-processing, the unit process data sets include about 7,000 types of flows and 2,500 unit processes. For the data, each value in the data set represents the amount of a specific type of intermediate flow or elementary flow associated with a certain unit process. For the first similarity-based link prediction method, the intuition of our method is based on the fact that similar processes should also have similar flows. Thus, if the knowing part of a unit process is sufficient, the observed unit process data, although they are not complete, they can potentially be used to extract the structure features of the underlying technology network. And in turn, such structural features can be used to predict the structure of the unknown area of the technology network. This procedure is quite similar to the friend's recommendation in social media. The similarity-based methods mainly have three steps. The first step is to measure the similarity between each pair of nodes in the network. In our model, we use the Minkowski distance to evaluate the distance between the different unit processes, and then we calculate the similarity by using its inverse. After that, we estimate the missing data using the weighted mean of the k most similar processes. This method is also known as the k-nearest neighbors, the KN method. The overall model performance is evaluated using the mean percentage error. For all the parameters in our model, the best ones are selected using the leave one out cross-validation techniques on the training side. So based on our results, we can see that when less data are missing, about 1% to 5%, the mean percentage errors are distributed in relatively narrow ranges, and our model performance can reach to a very high accuracy. And however, when more data missing, like to 10%, the distribution of the mean percentage errors becomes much broader, and our model performance can vary greatly between different unit processes. And when the missing data exists a certain level, certain threshold, like 20%, the known information is not enough to support the model to find the true nearest neighbor. And thus, the similarity-based methods are hard to estimate those missing data. So here we have a quick summary for the similarity-based method. As we can see from the results, the similarity-based link prediction method is a promising method to estimate missing data in LCI database like the Eco-Invent. So it also has certain pros and cons. For example, this method is quite easy to implement and can have very high accuracy when very less data missing. However, it also has outliers cons. This method has a strict application domain. And if there is no such similar process exists in the training set, this model can't provide any reasonable estimations. Also, this method can't handle the situation when more data are missing. So these findings inspire us to try to find other methods to solve the above challenges. So in order to solve the mentioned challenge, we construct another more flexible framework to estimate the missing data. The core assumption of this method is that the intermediate flows and the elementary flows are somewhat correlated with each other. More specifically, certain type of the intermediate flows are always accompanied with other intermediate flows, which means like the certain techniques are always show up together with other techniques in certain unit processes. And a certain structure of the technology framework, which means the intermediate flows, are related to certain types of resource consumption and emissions, which means the elementary flows, and vice versa. This means like if we use certain techniques, they always have certain types of emissions and energy and resource consumptions. So this ensemble of such interactions can be used to characterize the complex nonlinear relationship of these flows, which also enable us to use the known part to estimate the missing part. So the basic framework of our method can be divided into two steps. The first step is a kind of a classification model to identify whether an elementary flow or intermediate flow exists in the target unit processes. Then for those identified exist flows, a regression model is constructed to estimate their numeric values. Specifically, not like the similarity-based model, which can estimate all the missing part at the same time. In this model, for each missing flow X in the missing part P, we use all the non-missing I minus P variables in the training set as the predictors, and each missing flow X in the missing part P as the response. Thus, the predictors of the model will vary according to the missing data, and hundreds of independent models will be constructed. So based on this two-step framework, we tried different machine learning techniques to realize our classification and the regression task. As shown in the results, the extreme gradient boosting, the XGBoost model shows the best performance on both classification and the regression tasks with the least computational time. And the computational speed achieved by the extreme gradient boosting method is mainly due to the automatic usage of the multi-thread of the CPU to perform parallel calculations. And for the artificial neural network, in this study, the artificial neural network model was specifically the multi-layer perceptions. It shows promising performance on both classification and prediction results. However, it has more parameters to turn and requires substantially more computational time for the model to coverage. And compared with the random forest that has a slightly lower prediction accuracy, but requires a significantly less computational time. And this mainly due to the less hyperparameters it needed. And for the support vector machine, the SVM model, it performs the worst among our models and has a substantial computation time similar to the neural network. So based on these results, we finally selected the extreme gradient boosting and the random forest model, these two tree-based methods as our candidate methods. So by implementing these two tree-based methods for the classification task, the overall misclassification rate is less than 0.32%, which is an extremely low rate. And for the regression task, even for the situation for more than like 13% of the data missing, the model can still maintain a reasonable accuracy with an R-square about 0.62 and a mean percentage error less than 40%. So the model will not lose its prediction power until like more than 15% of the data, half of the data missing. Thus, this decision tree-based model can work as a complement to the previous similarity-based link prediction model to effectively estimate the missing LCI data when more than 10% of data are missing. So finally, I will talk about the conclusion of our study and some potential studies in the future. So in our study, we provide a prototype for using machine learning to estimate missing data in LCA studies. Those still have certain limitations. We can say like the machine learning models are promising in this area. For the future studies, we plan to construct a more systematic and general framework to apply machine learning techniques in LCA studies. Because for now, like for each study, they use different type of models and using different framework and structure. So we want to have a very general one. And for another future potential studies, we try to apply our methods on other databases like the US LCA database, which is a national database, and also the GREAT, which is a database focused on the transportation sectors. And also we try to widen the application of our current methods. We can use our current method to do some data quality examination and also do some real like case study to use our method to predict for some emerging technologies. Currently, our current studies have been published in the Journal of Environmental Science and Technology. And if you are interested in our studies, you can find more details in our papers. And you are welcome to reach to us if you have any questions. And thank you for your patience and welcome to all the questions. Thank you.
Thank you very much for your presentation. We are able to welcome some questions now, if anyone has any. Yes. Okay, if no one, I have one question. In your model, is it possible to supplement the information with like a physical constraint, like the mass balance or energy balance?
Oh, thanks for your questions. Like for here, we didn't consider like the balance issues because like for here we only trying to for here like showed in this figure. Yeah, we only focus on like to estimate those like certain missing flows. So which means like we don't know the exact mass balance of maybe some techniques. We're only really interested in like only certain type of emissions or certain type of like technology used in this certain unit process. So our method is only focusing on to estimate those missing ones rather than consider the whole general like mass balance and other issues.
Okay, thank you very much for your answer. I had another question about the data collection method. Because you mentioned that we need to find alternative, and I wanted to ask you like how much this development here can be an alternative, because I mean most of the eco-event data at the beginning are coming from like processing a mix of data collection and processing data. So I mean, the AI here can help filling the, yeah, it's one of the first in the introduction slide.
Should be here, right? Like some data processing.
Yeah, even before, I would say. Yeah, challenges. The next slide.
Yeah.
Yeah, as you mentioned, the current data collection methods are very expensive and time consuming. And that's the reason why you have a missing data in the LCA and LCIA. So we can rely on this development to fill in the missing data. But do you think that there is also after that a further need to be confirmed any time with like more traditional methodologies?
I think that this method can be specifically used in the situation like when some certain like test time consuming, like for certain flows, and if we want to test this kind of emissions, and this specific task maybe is dangerous, like there are some toxicity, liquid risk, or some certain like issues like that. And for this specific certain task is time consuming. And we know all the remaining parts, like some general information about this specific unit process. We know like the technology network of this process, and we know all the like the basic general emissions of the data. We only focus on like want to know some certain types of emissions and maybe energy consumption that we're really interested in. For that situation, our model can be applied on these situations. But our method still need to like collect some improved data to like we need some predictors. That's the issue. We still need to collect all the needed predictors that we need to get our response. So our method for now is still can only be used as like a complement. We can't totally replace all the current data collection method, but we are just trying to help to try to reduce their potential to reduce the time on those specific tasks. This is our purpose of our current studies.
Thank you very much for your answer. I would like, if there is no question for the audience, I would like to move with the next presenters. Once again, thank you very much for your presentation.
Thank you.
So the next presenter should have been Thomas Chen, but he has not connected yet. So I would like to move with the next presenter, Elisa Emma, and then this is a video that I will share with you in a second.
Hello, my name is Arisa Emma from the University of Tokyo. My academic background is science and technology studies, and I currently work on AI governance issues. Today, I would like to give a presentation entitled From Principle to Practices, Building an AI Governance Ecosystem. In addition to my academic hats at the University of Tokyo and Riken AIP Center, I also wear a hat of one of the board directors at the Japan Deep Learning Association, a nonprofit organization consisting of Japanese AI companies and startups, and also a member of the AI-related committees of the Cabinet Office and the Ministry of Internal Affairs and Communications. Today, I will be giving a presentation based on my activities at the University of Tokyo and the Japan Deep Learning Association. I would like to consider the relationship between practices and principles mentioned in the title of my presentation. I said principles to practices, but in reality, the arrow between principle and practices is mutual. In thinking about principles, the important points are how, what, and who. There are a number of ways to put them into practices, but I will focus on best practices, governance ecosystem, and technologies. First, let's open up principles. These principles are meaningless if they are created with a bias toward a particular stakeholders. Diversity and inclusions are important. In this regard, Japan sadly had some challenges. For example, in the social principle of human-centric AI, released in 2019 by the Japanese Cabinet Office, only 13.8% of the members are women, including myself. The EU's Trustworthy AI report, released around the same time, has an almost equal gender ratio. When it comes to principles, the focus tends to be on what is being discussed, but AI will be used by everyone. Therefore, it is very important to know how and who is discussing the topic to decide this content of what. Also, sector-specific discussions are currently underway. Since there are individual issues in sectors such as healthcare, mobility, and law enforcement, it is still important to discuss these principles. The discussion of principle for AI has begun around 2016, and I think there is a general consensus on what values are important. This table shows a typology of principles from various reports published by organizations in industry, academia, and government. One was compiled by the Harvard University and the other by the Chinese Academy of Sciences. It is easy to assume that two worlds, the West and the East, have different perspectives, but the fact that they refer to almost the same documents shown that they are generally the same in terms of their classification. Next, let's expand on practice. Currently, various organizations are releasing and sharing case studies on best practices in utilization and future employment or future work. Furthermore, challenging research is being promoted from the technical perspectives, such as trusted AI and explainable AI. In particular, from the perspectives of next AI, I believe that the utilization of AI combined with brain science and quantum will be an area where technological breakthroughs are expected. Just as important as case studies and technological development, building an AI governance ecosystem is also important. To explain this, I would like to first consider the industry structure surrounding AI systems. Earlier, I mentioned that various organizations have published principles and case studies of AI governance, but at present, it is mainly the huge business-to-consumer B2C companies known as platformers, such as Google and Amazon in the US and Tencent and Alibaba in China, that are providing notable AI service and products. And they are leading the discussion on AI governance. Although the principles and tools they have developed for AI governance can be helpful, it is sometimes technically and economically difficult for small companies and startups to implement similar governance systems. In particular, in recent years, the ability to develop AI governance is becoming an economic barrier to industry, as government procurement requires including the ability to develop AI governance within companies. On the other hand, in Japan, for example, AI is mainly used in the manufacturing industry. In addition, due to the industrial structure, Japan has many business-to-business B2B companies rather than B2C companies. And in the development of AI services and systems, data acquisition, data model development, and AI service provision tend to be done by different actors. This makes the issue who is responsible when an accident occurs in the course of providing services more difficult and more important. The question of where the responsibility lies is more serious, especially since AI has features to learn. For this reason, in Japan, the Ministry of Economy, Trade and Industry created contact guidelines showing several contact types. The guidelines for version 1 can be read in English, and right now they are publishing version 1.1. As you can see here, there are 3 possible types. In general, when we talk about AI governance, we mean governance within a company or organization, like corporate governance. However, in the case of an industrial structure with such a long supply chain like B2B, as explained in here, it is important for a single company. It is also impossible for a single company to establish a governance system that can respond to risk or the incident. Therefore, in this presentation, I will extend the framework of AI governance and propose a framework to form an AI governance ecosystem consisting of not only companies, but also a private and industry association, public sector, users, and also academia. Since last July, the Japan Deep Learning Association has been holding a study group with people from various external organizations who had been thinking about the evaluation and utilization of AI. These include auditing, insurance, standardization, whistleblowing systems, consumer protection systems, accident investigation, third-party committees, policy and social systems, monitoring, advertising, open data, and security. The speakers are from the industry and also the government and each organization. In addition, the topic of corporate AI governance attempts in traditional large AI companies and startup company was also discussed. The discussion of these workshops or the study group are currently in the process of being written, and it will be available in English in this July. Some of the reports have been already translated into English, so if you are interested, please visit this website. And also, the final report will be released in English in this July, so those who are interested in, please visit the website after July 22nd. Furthermore, as shown in this slide, the question of which external organization to collaborate with will also change during this R&D stage, or the utilization stage, or the incident stage. In this way, the concept of AI governance ecosystem is to think not only about governance within the company, but also about assessment criteria in the external environment or the organizations. What became clear in this study group is that these external organizations are also currently not ready for AI services and are seeking to reconfigure their existing frameworks. How can we audit or create insurance products for AI systems that have various characteristics, such as learning or becoming black box, and the difficulty of quality assurance? What this study group also revealed is that most of the Japanese laws address physical and financial damages, but there is still room for research on psychological damages. Psychological damages are challenged for the issues such as fairness and fake news that are currently being raised over AI systems. So far, I have mentioned that it is important to think about AI governance in the framework of an ecosystem with the external environment and organizations. But then, how can it be shared among different actors or the stakeholders? We believe that we need a framework for this purpose as well. In the AI governance project at the University of Tokyo, we have developed a risk chain model as a risk management tool for companies, and we are now collaborating with various companies in Japan. We believe that this will contribute to ensuring the liability and transparency of AI services and products among the various stakeholders. The RC model is structured into 3 layers: AI models and systems in green, the service provider in blue, and the users in orange. After gathering these stakeholders, we firstly identify critical risk scenarios for that AI service. Rather than a huge checklist of hundreds of items to evaluate all AI services, we take an approach of define the vision and the values of the companies and the AI services first, and then examine the risk scenario that may hinder the realization of these vision and values. For the identified critical risk scenarios, risk control is considered not only for the AI model, but also related technologies, service providers, and users, so that risk management plans can be developed for the entire AI services, even for the risk scenarios that cannot be adequately addressed by an AI model alone. For each risk scenario, we then examine the risk factors as each layer of the model and draw chain, considering the order in which the risks occur. Risk controls are discussed among the parties involved in each of the elements, each of the factors associated with this risk chain. No single risk control may be sufficient to reduce the risks, but it does not have to address all risks. The risk chain model approach is to consider the optimal risk control based on the magnitude of the risk and its cost effectiveness. In this way, we can expect to have a common understanding among all parties and stakeholders involved. We are currently creating case studies of such as unmanned convenience stores, recruitment AI, power line inspection AI, and etc. We plan to publish these on the University of Tokyo's website, along with a Japanese and English guidebook on risk chain model from this July. We are also planning to release a video of risk chain model discussion with English subtitle this autumn. In addition to this talk, the University of Tokyo is also developing an AI governance project. We have published a report on AI and governance and COVID-19 in Asia, and also more broader discussion on AI principles to practice. And also, we published a report on scenario workshop for students on facial recognition systems organized with the UN Department of Disarmament Affairs. On this year, we are also planning to conduct research on social impact on cyber agent, especially on the operation of teleexistence cases, such as Robot Cafe, that will open this June. So today, this is all of my presentation, and I really would love to hear the feedback. If you are interested in, please check out our website for more details. So I look forward for the further collaboration with you, and thank you very much for your attention. Have a great day.
So thank you. That was the presentation of Dr. Lisa Emma from the University of Tokyo. I would like to continue immediately with the next presenter, Magdalena Ruch. And I also have a video for the occasion. So I would like to share the video too.
Hello and a warm welcome to my today's presentation at the Industrial Ecology Days 2021. My name is Magdalena Ruch, and I would like to use the next minutes to present some insights we gained from a study about the application of digital technologies for circular and sustainable product management. The co-authors of this study are Josef Schöckl and Professor Rupert Baumgartner. First of all, I will quickly give you an introduction to our research lab for sustainable product management, enabling a circular economy. I will provide you with a bit of background information and then continue with the method, the results, and the conclusions of our study. I am part of the CD lab, and in our project, the goals are to operationalize the generic meanings of sustainable development and circular economy on the corporate and product level, to use the potential of digitalization for sustainable product management, and the study I will present today is part of this work package, and also to understand decision-making processes in companies and in supply chain networks as basis of a lifecycle-wide implementation of sustainable product management. The aim of the study lab is to support companies with new and improved methods and concepts for the collection and use of environmental and social data for circular product life cycles in sustainability assessment and design. Before I talk about our study, I will give a bit of background information on how we understand the term sustainable product management. We use and see it as an umbrella term that comprises practices such as sustainability assessment, sustainable supply chain management, or sustainable product development. The specifications of SPM in a circular economy are that also circularity assessment and closed loop supply chain management play a role, as well as the consideration of the 10 R's and different design strategies help to operationalize SE. Sustainable product management practices share a comprehensive life cycle perspective and the inherent dependency of the exchange of material and product related information. Today, I will present some insights we gained from an exploratory research study that combined a keyword-based systematic literature review with quantitative and qualitative content analysis of selected papers. We focused on the scientific literature on the intersection of two fields. First, we used digital technology terms like artificial intelligence, Internet of Things, big data, or blockchain, and then combined them with keywords from the SPM field like circular economy, sustainable supply chain management, or eco-design. In our study, we found around 330 journal articles that combined these terms. And from this sample, we selected 186 articles for a qualitative content analysis. In total, we identified 146 application examples, of which 80 examples are described as potential or conceptual examples, and 66 examples were found where the digital technologies are actually applied in practice or where a case study was conducted. And now we switch to the results of the study. We identified different business areas in which the before mentioned technologies can be applied or are already applied. We categorized the examples based on their main point of contribution during the life cycle of the product, divided into the beginning, middle, or end of life stage. On this slide, you can see the selected examples from the application of big data analysis and IoT for sustainable product management uses. What stands out here is that various applications address the issue of optimization and efficiency advancements with the goal of reduced costs or reduced material or energy used. For example, the increased efficiency of the energy use of equipment was mentioned, and also maintenance issues are discussed quite often. One example is predictive maintenance to avoid larger damages on machines and thereby enable a lifetime extension of products. Or an example from practice comes from Rolls-Royce. They use preventive and predictive maintenance to extend the useful life of engines by monitoring the engine data received via satellites in real time. What also is interesting here is that big data analysis could be used for improved product design, which is a key area in circular economy. The company HP, for example, can monitor the ink levels of their printers and automatically order a new cartridge and at the same time an envelope to send the old cartridge back. Also, data from products in use support here the design decisions like the design for durability at the firm HP. Next, we identified applications for artificial intelligence and blockchain technology. Blockchain offers a lot of potential to track sustainability compliance along the supply chain and enable inter-organizational information sharing in a reliable way. And for AI, the least examples were actually found in literature, but an interesting one could be that AI is already used for lifecycle inventory data collection, or AI also can be used for waste sorting based on picture recognition. By using an inductive coding approach, we assigned the 146 examples to main areas of SPM to understand better which of these areas may benefit from the use of new digital technologies. We identified 4 main areas, which are supply chain management, assessment, product design, and business model. Several examples, however, were not directly related to such activities, but often serve as enabler or facilitators for more than one specific SPM activity. For these examples, we use the category SPM General. In addition, we extracted from the analysis also how these digital technologies benefit sustainable product management. We identified that the 146 examples cluster around the topics of transparency, efficiency, trustworthiness, and also here a category for more general examples was used. Starting from the right-hand side, it can be seen that IoT cases are most often reported in literature, and the majority refers to the general SPM category, as the IoT sensors that are used throughout the life cycle can serve as information providers for various SPM activities. What can be seen here also is, when looking at the outcomes illustrated by the colors, is that IoT and also big data and analytics mainly provided or increased the efficiency in existing operations. Blockchain technology enables, in most cases, increased transparency and trustworthiness between stakeholders, as it may increases the value chain actors' willingness to share potentially confidential environmental and social data. This heat map adds an additional layer of detail to the analysis by illustrating which specific activities of SPM are potentially supported by the use of technologies. Compared to the results shown in the slide before, we provide a much higher granularity of SPM activities. On the left side, you see the 4 DTs that we have included in the study, and horizontally at the bottom, the main SPM activities that we have identified. It shows the relative share of specific SPM activities per digital technology. For example, for AI, 4 examples were found, and those are focused on lifecycle inventory tasks, smart supplier selection, condition monitoring of products, and on the end-of-life phase of products. For example, in the end-of-life phase, AI could support the waste separation activities, and by doing so, enabling different R strategies. The most frequent use of IoT technology refers to its use for maintenance, for example, for the manufacturing equipment of companies. And also, IoT sensors have great potential for condition monitoring by capturing data of a product's real-time status. Other examples are location monitoring to identify potential risks of shipment delays, or one used by the company Whirlpool is that they sell washing machines that give the user notifications about upcoming maintenance needs. Last but not least, the Resolve framework from the Alan MacArthur Foundation was used to categorize the examples based on their main contribution to one of the 6 circular economy strategies, which are resolve, share, optimize, loop, virtualize, or exchange. For this analysis, we separated the potential or conceptual examples from the examples that are already implemented, here referred to as applications. The assessment and allocation of digital technology examples in terms of the Resolve framework showed that the strategy Optimize, which relates to increasing product performance and efficiency and to removing waste from production and supply chains, is by far the most frequently discussed one. This shows that so far, digital technologies are often used for incremental improvements of products and processes, but other result strategies that entail more radical changes to, for example, business models or processes are less frequently described so far. To sum it up, it can be said that various levels of corporate sustainability and circularity management practices can potentially benefit from the use of digital technologies. For example, the identification, collection, and sorting of materials, as well as the tracking of products, can be facilitated by these technologies. All the design of products can be supported, as the design for durability example of the company HP showed. Increased efficiency in production operations, but also in logistics, can be achieved, and examples like Philips Light as a Service show that product service systems can be enabled by the use of digital technologies. However, so far, digital technologies are mainly used for value creation. That means operational performance and efficiency. And significant changes of the value proposition and the related capturing of value for example, the virtualization or a shift to more product service systems, are still seldom. For more information on this research study or other project from the CD laboratory, please check out our website circular.uni-graz or also reach out to me via email. Thanks a lot for listening, and I'm looking forward to the rest of this interesting session.
So thank you very much to Magdalena for this presentation. She's also here, so we can ask her some question. We have some time to ask some question if any one of you has any question.
Yeah, Franco have some question, I guess.
Yes, so please, Franco.
Hi, thank you for the very interesting presentation. I was wondering, how do you see the implementations of, or in ways the use of these technologies, how it will change depending on the sector, and whether there is a difference in the implementation of these solutions for small, medium enterprises in comparison with larger corporations, for instance?
Sorry.
Now, yeah, now it works. Can you hear me now?
Yes, we can hear you.
Oh, great. Yeah, sorry for the delay. I was not able to unmute. Thanks for your question. I think this is a very interesting one. And so for in literature, we have seen that it's a very clear focus on big corporates. So mostly, like really a majority of the examples found that describe the use of digital technologies in corporations are from big corporations. And I think this is mainly because they have the capacity on the human side, but also monetary to do so and to invest in new technologies. And with the smaller companies, I think this is, still, this is, at least in literature, still lacking. And I think this could also be the issue because they just, at the moment, lack the resources to try out new ways, for example, of product design enabled by digital technologies, or also these resource efficiency optimization strategies are not so, maybe also not at the moment so important for them, or at least not enabled by digital technologies. Maybe they find other ways first. But when the digital technologies become more accessible, I would say this then also plays a more relevant role for SMEs. And I think this will also then be kind of seen in literature later, but yeah, very relevant for SMEs as well. And at the moment we are conducting another study and we ask manufacturing companies in Austria how mature they already in digitization strategies. I think this, it becomes a clear trend, or we can see already that most of the projects are in a pilot phase and not ready yet for implementation, but pilot phases are already there.
Okay, Magdalena, thank you very much for your answer. I also have a question from my side. This is one of the slides that you share on your video, and what is very struggling is the way the artificial intelligence is quite seldomly used compared to the others, and I would like to know if you have an explanation of an idea for this comparatively low use of artificial intelligence compared to the others.
So what was very interesting when we did our literature keyword-based search was that AI really appeared a lot. And we actually expected that there are many artificial intelligence examples in this area, but unfortunately, most of the terms found were not related to examples, but more related to sources or references. So this was a bit misleading, actually, I would say. But then why this is then so little talked about in literature, I mean, it could be that the field here is maybe not only focused on this keyword, right? So there are a lot of other keywords around, like we heard in the first presentation, that also artificial neural networks will play a role. And at one point we had to say that we have to make a cut in the keywords we use, but I think it could be really interesting to only focus then in one study at artificial intelligence and kind of really focus on this area and not have this broad scope. I think it was very good for starting to include a lot of keywords in the digital technology area, but for really maybe only focusing on one technology, like today on AI, this could also be very interesting.
Okay, thank you very much. We have time to take a last question, so I will ask Tamer.
Hi, can you hear me?
Yeah,
yes.
very well.
Thank you. It was very interesting. My question is, how many of these research are for potential and how many are for actual application that are being used?
Yeah, thanks for the question. From the 136 examples, there were 80 where already we found either a company example, for example, like the examples I mentioned in the presentation, HP or Rolls-Royce or others, or a case study was conducted, and 66 were described as conceptual or framework or not implemented yet.
Oh, it sounds like a good number. I was surprised.
Same for me, yes. I expected a much lower number for the already implemented cases, but actually there are quite some described in literature already.
Okay, thank you very much. If it's okay, I would like to move with the next presenter. Oh, Franco Donati, are you ready?
Yes, I am.
Thank you very much, Magdalena, for the presentation.
Okay. Well, perhaps not fully. Just 1 second. And then share screen. Can you see my screen?
Yeah, yes, we can see.
Wonderful. Thank you so much. My name is Franco Donati. I'm a PhD student at Leiden University, and I'm going to talk to you about automating lifecycle inventory phase using computer technologies and artificial intelligence. There's a systematic review that we've been conducting. So the main question is, can data for lifecycle inventories be increased through the use of computer technologies and artificial intelligence? We believe that there is a wealth of information that is generated across the life cycle of products, so starting from product lifecycle management tools such as computer technologies. And artificial intelligence applications offer a lot of potential for automation and connectivity. And we think that the combination of these two could be instrumental in generating more data. Okay. So why is this important? Only a very small fraction of products are environmentally assessed. new products don't have an environmental impact benchmark to refer to, so this limits innovation and competition. But most importantly, there is a disconnect between the urgency of the ecological crisis and the availability of production data for environmental impact assessment. We start from the life cycle inventory phase, and we use an adaptation. Well, there is an adapted figure from the EPA and the Handbook of Life Cycle Inventory, where we have the stages of life cycle inventory, of life cycle assessment, and the inputs and outputs through these stages. So the elementary flows and how they are subdivided. Computer-aided technologies are a set of technologies that allow for design, analysis, and manufacture of products, and they're really the backbone of modern product development. But they are a large ecosystem of technologies. In our study specifically, we focus on 5, which are computer-aided design and computer-aided engineering, which focus on the first on the design of a 3D model of 3D design of of products and parts, and computer-aided engineering, on the other hand, allows for the assessment of performances under different stimuli of parts. Computer manufacturing, computer process planning allow for the planning and identification of manufacturing activities and how they come in sequence. And then computer process engineering, which focuses on the design and optimization of chemical processes. And then we look at the artificial intelligence, and specifically we look at the expert systems, machine learning, and data mining. So we want to know the knowledge-based systems that once they are provided with a expert domain knowledge, they can match or exceed human experts. Machine learning, so the ability for computers to adapt and to learn by experience and additional knowledge, and then data mining, so like knowledge discovery in databases. But of course, there are many other applications in artificial intelligence. The methods of the review, we asked 2 questions which resulted in 2 searches. One is how can computer technology tools be used to compile lifecycle inventories, and how can artificial intelligence application be used to compile lifecycle inventories? And we combined the results of these 2 searches. In the literature, we see that doing a network analysis of the literature, we see on the left-hand side here a circular graph where computer design, computer process engineering, machine learning are really dominant in the literature of how we're using these techniques for lifecycle inventories. And then there are, of course, also some connections with other techniques, but they become a little bit more. They are a little bit less investigated. On the right-hand side, we divided. You see a network analysis of how the sectors relate to the different use of these techniques. And we see, for instance, the physical goods, so anything that can be a mechanical part or a consumer product that has a physical form. Really makes use a lot of computer design, computer manufacturing, engineering, and process planning, whereas the computer process engineering, of course, focuses on the chemical sector. However, while we see the machine learning is broadly used, for example, in the chemical sector, a little bit in construction, the use of machine learning for physical goods, for the estimation of physical goods, lifecycle inventories, that is still missing. And there is a little bit of work being done in data mining and expert systems that are connected to computer designs and the design of physical goods. We analyzed then how the studies in which parts of the life cycle stages and which type of elementary flows we could obtain using these different technologies, and we see the manufacturing phase. The manufacturing stage is actually the most predominant one, and of course that's normal because these technologies, for computer technology specifically, they are mostly used for manufacturing planning and designing products. However, we can still estimate some of the values that are related to other stages, and I'll explain in a second. In principle, we can obtain a lot of type of information that is useful for elementary flows in using computer technologies. We can figure out the type of activity that is being taken in consideration. So the processes, the materials, the energy and goods. But of course, as we move towards, well, not of course, but as we move towards environmental interventions, that becomes a little bit more difficult to assess. As you can see, the flows over here, they're a little bit, they're smaller. So stages compilation using computer technologies, we see that in the resource acquisition phase, there is a very limited use and expertise and simulations are needed. In the manufacturing and construction stage, we really rely on feature technology and flow sheeting and ontologies to make sure that the data is transferred. Feature technologies is essentially how the shape and the shape of 3D models are then categorized for planning manufacturing, for instance, or to extract information from 3D models. Flow sheeting instead refers to computer process engineering and how the energy balances and mass balances are organized to make a computer process engineering function. And then ontologies can really be instrumental to extract this information and translate it to lifecycle inventories. It is important to actually, the process and material databases are very important to make sure that this information is available. We didn't see any information on the distribution stage. And but we saw that in use, reuse, and maintenance, and the waste management and recycling, there is a vast use of design for X methods and lifecycle design methods, which use essentially computer technologies with some methodological estimation methods or design methods that are not necessarily computer based, that to estimate what type of services or what type of end of life processes they might be involved. With artificial intelligence, on the other hand, we see a broad use of these applications for resource acquisition, mostly when it comes to agriculture, and there is a lot of potential for spatial explicitness and future scenarios. At least that's what the literature has shown. In manufacturing and construction, data mining approaches seem to be quite effective in generating data for lifecycle inventory, specifically, mostly though in the chemical sector. And expert system ontologies for domain-specific transfers or automation are also quite important. So I have a database of chemicals, for example. How do I translate that into lifecycle inventories? There is a very limited application also in the distribution phase. However, there was some studies that showed that the big data and regional data sources can be useful to complete this part. And use and reuse and maintenance and waste management and recycling, we can artificial intelligence can be used to predict and generate thousands of alternatives, and as a result also figure out the uncertainties that are related to certain values. We can cluster consumer behaviors, but also identification of waste treatment and regional waste projections. In conclusions, computer technology can be used to obtain lifecycle inventories, but most appropriate in the manufacturing stage. The nice thing about computer technology software is that it can be used in orchestration with other computer technologies, but also independently, which offers a chance for automation independent from industries. But in order to estimate the remaining lifecycle stages, we need to employ other methodologies to get the data. Artificial intelligence methods are useful to automate data exploration for lifecycle inventories. And we can generate alternatives and uncertainties thanks to these methods. However, there's a need for diverse set of data, and expert systems need to be further developed. There are good opportunities to combine computer technology and artificial intelligence techniques for lifecycle inventories. But more applied research is needed to explore this combination, and there are definitely a lot of opportunities. For example, computer technologies already make use of artificial intelligence techniques to estimate process planning and manufacturing. However, it is not used for life cycle to obtain data for life cycle inventories. The future work is to develop a system that can provide detailed, however minimal, digital twin of supply chains, connecting computer technologies tool to lifecycle inventories, and possibly use publicly available data. We need to create more expert systems with rules for the creation of lifecycle inventories, and perhaps web applications for collaborative use of cards can be used to obtain lifecycle inventory data. We should explore also remote sensing and crowdsourcing solutions to see how we can fill up the data gaps, essentially, for example, both in the distribution and resource acquisition phase, but also in classifying the data and organizing it. So we don't necessarily need to do it all by ourselves. And then there are issues of interoperability. So more research needs to be done on ledger-based common ontologies and standards to make sure that data is adequately transferred. And this is everything. Thank you so much.
Thank you very much, Franco, for presentation. I am welcoming a few questions. If there is anyone, please feel free to ask question.
Actually, I would have one. In the conclusions, you said that AI is already used for plant engineering or computer-aided plant engineering, for example, but not for LCI yet. Do you know, or do you know any reason for that? Why this is not yet a thing?
I'm sorry, I wasn't able to understand the question. Could you repeat it?
Yeah, sure. In the conclusions, I understood that AI is already used for plant or computer-aided plant engineering, right? You said, but not yet for LCA so much. LCI, and you said there is for sure opportunity for future research, but why is it not yet a method that is applied? Because it seems that it offers a lot of opportunity for LCI. Do you know any reason for that?
Yeah, I mean, I only can offer speculations, but my position is that I think that just the two communities are not really they're not really talking to each other that much. So a lot of work that has been done in computer-aided technologies it remains within and process planning. It remains within that community, but it is perhaps the lifecycle assessment community is not really reaching out, just like they are not reaching out perhaps on the other side. So I think that is really personally, I think that's the reason. However, I'm not I cannot offer citations for that.
Sure. Yeah. Thanks. Very interesting. Yeah.
Thank you.
And thank you very much, Franco, for your presentation. I would like to welcome the last presenter, Jacopo Testi. Correct.
Yeah, sure.
Welcome.
Hello, everyone. Very nice to meet you. And thank you for having me today. So first of all, I'm sharing in the chat my project's link in case you'd like to have a look at it while I'm presenting. And now in 2 seconds, you should see my screen. Can you properly see the presentation?
Yes.
Okay, great. So hello, everyone. My name is Jacopo, and I'm currently working as urban artificial intelligence scientist at RIA Group and as advisor at Urban AI. The work that I'm presenting today will be published by the Deep City, Climate Crisis, Democracy, and the Digital within the session Resilient Cities, and by the Machine Learning, Artificial Intelligence, and Urban Planning publication. Urban Forestry Science was a project nominated as winning proposal by the Bruno Kessler Foundation and Climate KSE, and the work was sponsored by European Space Agency satellite data and selected by the ESRI Geo-Observatory 2021. So the theoretical framework of the entire research is inspired by the general theory of urbanization published by Alfonso Cerdà in 1867, which is, let's say, considered to be the first text in history that presents urbanization comprehensively as a science. And Cerdà represented surely a faithful reflection of his time, when the early effects of the Industrial Revolution were changing the social, economic, and cultural relationships in society. Cerdà planned his book in 4 volumes, but he ultimately only published the first and the second volume, in which he expanded his work with a more scientific and structured approach in order to basically understand how statistical information about the different layers of the city could provide an understanding of the challenges that cities were facing at that time. Also, since the mid-20th century, ecology and urbanism have begun to converge as researchers began to study the impact of urban phenomena on the planet. And now that the effects of climate change are undeniable, the integration of these two sciences, urbanism and ecology, is accelerating. So I'm referring to Cerdà because he intuitively included in his theory multiple references to the idea of the urban organism as an advance of our urban ecology, which studies the city as an ecosystem. Similarly, today, what we are facing, as the economy Jeremy Rifkin defines it, is a third industrial revolution that is fundamentally changing the way we manage power and move economic activities. In this historical context, data and ultimately information appear to assume an unprecedented economic asset. And indeed, the amount of data produced yearly and foreseen to be produced is enormous, as you see from this histogram. So, keeping this broader research context in mind, the proposal's objective was to unfold a strategy to identify optimal locations in the city of Madrid for future urban tree canopy using public available data. As everyone knows, trees represent a fundamental economic, social, environmental asset for our urban areas. So the green canopy infrastructure provides multifaceted benefits for the planet and citizens, such as particulate matter removal, temperature reduction, noise pollution, flooding prevention, whether in parks or along streets. This is the reason why the research correlates environmental data with the purpose of defining the environmental discomfort index. The statistical composite indicator provides insights regarding the environmental conditions of Madrid districts in 2019, which was considered as a more robust for the methodological approach. As everyone knows, in 2020 and 2021 might represent an outlier for the current condition that we are all living. So what do we mean by a statistical composite indicator? A composite indicator is formed when individual indicators are compiled into a single index on the basis of an underlying model. And the composite indicator should ideally measure multidimensional concepts which cannot be captured by a single indicator. So basically, the just described let's say what I have just described is the first and crucial step, which is defined by the theoretical framework. What was selected next were the so-called elementary indicators, as I said before, that are composing the multidimensional metrics via a subjective approach that relies on the domain expertise. On this slide, indeed, you can see all the information that was collapsed within the final index, namely carbon monoxide, noise pollution, particulate matter, precipitation, solar radiation, temperature, and tree density. Most information is tabular and structured data in the form of probabilistic samples as a primary source of Madrid municipality. All these features characterize our multidimensional index, and for clarity, they are indeed organized as a matrix composed by all different urban zones, as you can see on the left side, and they are observations, and as many columns as the number of elementary indicators. The task then was to carefully observe the linear correlations between all indicators in order to avoid redundancy within our final outcome. In fact, if two datasets have explicit positive or negative linear correlation, they are similarly describing our phenomenon. Thus, eliminating one of them results in dimensional and noise reduction. As you can see from this slide, in these specific circumstances, we do not have highly correlated features. After having performed a multivariate analysis in the form of a correlation matrix, what it was needed to reduce all elementary indicators to the same units. Therefore, it was applied Mpi normalization. Fundamental to notice is that this is a transformation that happens only vertically, standardizing all indicators between 70 and 130. There are obviously many different types of standardizations and normalization. In this case, I used Mpi in order to assign the same weight to the indicators. Following the normalization, where, as I was mentioning, all indicators assume the same units, then I needed to aggregate them to finally compose the multidimensional index. Using Mpi aggregation, as you can see from the formulas, I sum the mean of all horizontal elements and the variance sigma. Once aggregated, the multidimensional matrix collapses into one unique number for each urban zones that describe the environmental discomfort index accordingly, as you can see from the vector on the right, which is basically the result. And finally, to verify the robustness of the composite index, I needed to perform an influence analysis by feeding a regression line between our index and each elementary indicator at each time is removed. And this analysis was helpful to observe the indicator's influence on the final outcome. This was also a final criteria to select normalization and aggregation methodologies, as Mpi process resulted in the most robust index. The final results displayed in the cartography here and publicly available on the link at the bottom right of this slide, which is basically an interactive cartography that I shared with you within the LINKS project, demonstrate that darkest areas with an index of maximum 115, representing very high environmental discomfort, which are respectively the urban zones of Sol and Cortez, followed by other central areas, while lighter ones have values around 90, as it is clearly visible in peripheral zones. After the first spatial analysis performed at urban scale, Santa Eugenia neighborhood was selected as it presents a notably high urban temperature. Therefore, a granular and detailed observations are conducted in order to detect optimal tree canopy locations. It is important to notice that in this case, the urban temperature layer was taken into account, but actually this methodological approach, it can be obviously scaled to all other layers that I mentioned so far. So in fact, it can be observed. The red areas are the ones identified with highest represented by the dark gray color and with no arboreal presence. For demonstration purposes, it is shown, as I was saying, the temperature layer only, but the methodology, it is applicable to all other layers identified. Finally, the proposal presents both some potentials and limitations that might be addressed with the assistance of artificial intelligence and specifically deep learning models. In fact, the methodology proposed has the potentials to be replicated throughout time. This approach would allow Madrid municipality to measure the environmental discomfort index and observe any changes in relation to policies adopted in the past, in the present, and forecast future impacts via deep learning models composed by convolutional and long short-term memory artificial neural networks. Moreover, TREE's dataset provided by the Madrid City Council could be drastically improved using satellite data. In this case, you see an example of a very high resolution satellite acquisition, which was provided, as said before, by the European Space Agency, which sponsored this project. And in this case, the dataset from the municipality was refined, utilizing deep learning for object recognition. And on this picture, you can see how the AI model, which is, let's say, the picture on the right, manages to integrate the tree crowns that are missing in the original dataset. Thus, this basically allow a more precise composition of the multi-dimensional index that was presented previously. And finally, I'd like to conclude with a famous quote attributed to Buckminster Fuller in the book Vision of Hope and Abundance for All, where he pronounces the following sentence: "We are called to be architects of the future and not its victims." So thank you so much for listening to the entire presentation. And if you have any questions, or if you are interested in the specific paper or integrate AI on urban planning research or operational pipelines, feel free just to contact me either on LinkedIn or my personal address that you find here.
Thank you very much for this presentation. We have some time for questions, if there is any. Okay, so for my part, I will have one question related to the diagram when you present the environmental discomfort. You are able to have a very detailed level of the different level of environmental discomfort in the city. Is it also possible to link this kind of environmental discomfort to social segregation, or and also for example, real estate prices, that we could expect?
Yeah.
Environmental discomfort will raise to lower price of building and normally poor people living in these areas?
Yeah, of course, this is surely possible, as long as, let's say, you have granular data as you have for the discomfort level. It is surely possible to either correlate or spatially correlate them within the urban zones.
Okay, thank you. Thank you very much. Do we have some question from the audience? Okay, if not, I thank you very much, Yapoko, for this presentation, and then I would like to thank all the presenters and the audience for joining this session. Please stay after this session because we have a panel session that will also give interesting insight discussion on the application and the future of AI in the context of industrial ecology. So if you have the link here, and it will start at about like 12 minutes at 4. So you have some time to grab something to eat, have a coffee or whatever. Thank you very much.
Okay, Sebastian, I will just
Yeah.
leave the room like open, just in case of like any other like participants might think that we are going to use the same room. So I will just open until like the new session open.
Okay.
Yeah, so they can see the link to that session.
Oh, I will. Okay.
Yes. Thank you, Sebastian.
Then I will connect to the other session.
Yeah. I will stay here until the beginning of next session.
Okay, thank you very much.